Well, my dear participants, now I am going to talk about the analysis using F22 package, analysis with FPP2 package. Actually, material of this section has been taken from the great book Forecasting Principles and Practice by Rob J. Heidman and George Athanasopoulos, University of Monash, Australia. They have the R implementation of this book in the form of FPP2. It is the second edition. 2 stands for the second edition, and they have developed separate packages for implementation of that book. FPP2 for second edition and FPP3 for the third edition, which is the third edition is available on Google also, on GitHub also. It is an open source book. Time series plots below shows, this book is a nice book, and that's why I wanted to cover from this book. It has very good graphics because it presents graphics from GG using ggplot2. So ggplot2 is the most attractive graphic, and that's why I prefer to describe these time series analysis with FPP2 package. Below, details you can have from the book. Below shows the weekly economy passenger load on Ansett Airlines between Australia's two largest cities, Melbourne and Sydney, in 1987 to 1992. Require our library FPP2, then head Melbourne and Sydney. So it starts from 1987, and end after start 1987 26 and then end 1987 31. Frequency is 52. Auto.plot is a function in this FPP2 package. Auto.plot automatically it understands what kind of plot should be given. So that is known as auto.plot. Now I will go into require FPP2 and see what else you want. You want about the data mail sheet. Help mail sheet. Mail sheet. See, total weekly air passenger numbers, it is in FPP2 package. Total weekly air passengers numbers on Ansett Airlines flights between Melbourne and Sydney 1987 to 1992. And this is the description. Air traffic numbers are in thousands and divided into first class, business class and economy class. There was a major pilot industrial dispute during the data period, resulting in some weeks with zero traffic. There was also at least 2 changes in the definition of the passenger classes. See, formula, source, and this is the auto plot. I would like to give the help of auto plot. Auto plot is a very useful function. Auto plot in the forecast with ggplot2. So we are going to have forecast, auto plot. auto plot. ggplot, partial autocorrelation function. See, so these are the autoplots. Autoplots objects, ggacf, ggpacf. So all these are there. Now I would like to have autoplot Melbourne, Sydney. This is the economic class. This is the column of economic class from Melbourne, Sydney. Plus GG title, economic class passengers, Melbourne, Sydney. Plus XLab year, because it is in the back end GG plot to work. So that's why it is in the form of plus and plus. So plus XLab plus YLab. So when we run, it gives the plot of the data. This is the time series plot in thousands from 1987 to 1992. Lag plots. Now I would like to discuss about lag plot. The following figure displays scatter plots of quarterly Australian beer production, where the horizontal axis shows lag values of a time series. Each graph shows Tk plotted against Yt minus k for different values of k. So here require fpp2, beer 2, window AU Australian beer, this is an object, it starts 1992. So first I would like to show you what is the help Australian beer. See, quarterly Australian beer production, it is in fpp2 package. Total quarterly beer production in Australia from 1956 quarter 1 to 2010 quarter 2, and this is a time series plot. So window actually it extract from, see, if we will have this data is from 1956 to 2010. So what we are having, we are starting here from 1992. We are not selecting from 1956. We are extracting data from 1902 onwards. And then we are having GG plot beer 2. So GG plot, GG lag plot. So it is lag plot, GG lag plot. Oh, this is the lag plot. For lag 1, this is the plot. For lag 2, this is the plot. For lag 3, this is the plot. For lag 4, see here, in lag 4, there is positive correlation, autocorrelation. Similarly, in lag 8 also there is positive correlation. Whereas in lag 2, there is negative correlation, highly negative correlation. Similarly, in lag 6, there is highly negative correlation. So this is the lag plot of the data, which we are getting through the function GG lag plot, which is a part of GG and fpp2 package. Now lag plots we have already discussed. Autocorrelation. Just as correlation measures the extent of a linear relationship between two variables, autocorrelation measures the linear relationship between lag variables of a time series. There are several autocorrelation coefficients corresponding to each panel in the lag plot. For example, R1 measures the relationship between Yt and Yt minus 1. This is the R1. Similarly, R2 Similarly, R2 measures the correlation coefficient, autocorrelation coefficient between YT and between YT and YT minus 2. It is YT minus 2. It is wrongly typed. The value of the RK can be written as, this is the K lagged autocorrelation. So this is the formula where T stands for the length of the time series. The first 9 autocorrelation coefficients of the beer production are given here. R1 is minus 0.10, R2 is minus 0.65, see R2 minus 0.65, which is negative. Similarly, R3, R4 is 0.869, R4 it is 0.869, and similarly R8 0.83 and R6 0.6, R8 is 0.83, R8 is 0.83 and R6 is just like R2. So, the autocorrelation function coefficients are plotted to show the autocorrelation function ACF. The plot are known as correlogram. This is known as correlogram. So GGACF. So this is the GG plot version of the function ACF Beer2. So this is the ACF. See, this is the value of R2, this is the value of R4, this is the value of R6, this is the value of R8, like this. And these are the 95% confidence intervals. Autocorrelation quarterly beer production. R4 is higher than the other lags. R4 is the higher than the other lags. This is due to the seasonal patterns in the data. The peaks tend to be 4 quarters apart and troughs tend to be 2 quarters apart. These are the troughs. R2 is more negative than the other lags because troughs tend to be 2 quarters behind peaks. The dashed blue lines indicate whether the correlation are significantly different from 0. So these correlations are significantly different from 0, but these are not because they are crossing the 95% confidence interval. Trends and seasonality in ACF plots. When data have a trend, the autocorrelations for small lags tend to be a large and positive because observations nearby in time are also nearby in size. So the ACF plots trended time series tend to have positive values, and that slowly decreases as lags increase. When data are seasonal, the autocorrelation will be larger for seasonal lags at multiples of seasonal frequency than the other lags. When the data are both trended and seasonal, you see a combination of these effects. The monthly Australian electricity demand series plotted in figure shows both trend and seasonality. The ACF plot is shown in figure C. This is the ELEC window. We have taken data from 1980 from ELEC and auto plot AE ELEC plus X lab Y lab. So this is the seasonality and this is the trend also. Monthly electricity demand. GGACF at lag 4. See, this shows positive correlation and that means the trend is like this, and this shows this ACF plot. This is the corresponding ACF plot which shows like this. Then we are going to talk about white noise. Time series that shows no autocorrelation are called white noise. Figure give an example of white noise. This figure gives an example of white noise. See, they are around 0 and they are simulated from, see, y is equal to Ts R norm. So we are simulating 50 observations from normal distribution, from normal 0, 1, and then we are converting that into TS object, into the TS object, time series object. Then auto dot plot y and GG title white noise and GG ACF. See, white noise GG title and then GG ACF. See here, none of the autocorrelations are outside this range. So none of them, even at lag 15, 18, they are not crossing these two lines, so they are not significant. For white noise series, we expect the autocorrelation to be close to 0. It is close to 0. Of course, they will not be exactly equal to 0 as there is some random variation, but they are within the limit. They are within the 95% confidence limit. For a white noise series, we expect 95% of the spikes in ACF to lie within the plus minus 2 by square root of 2. In this example, t is equal to 50 and bounds are plus minus 2 by square root 50 plus minus 0.28. So it is minus 0.28 and plus 0.28. Time series regression models. Simple linear regression model. US consumption expenditure. See, shows time series of quarterly percentage change growth rates of real personal consumption expenditure Y and real personal disposable income X from the US from 1970 quarter 1 to 2016 quarter 3. Auto plot US change. So this is the US change is the data, and this is the consumption and income. These two columns we are selecting, plus Y lab percent change, X lab year, and we are having this model. So this is the consumption, red is the consumption, and income is in this color. It is green color. And we are getting this plot by this command, US change. Fit the model. We can fit the model shown in the figure. So here we are plotting. We are just plotting. And then we are fitting this by making the function TSLM. LM is for linear models and TSLM is for time series linear model. Consumption versus income data is equal to US change, and these are the summary of results. So this is the income quarterly percent change, and this is the consumption, and this is a trend. So these are the multiple linear regression model TSLM, income, consumption, not only income, rather production, unemployment and savings, they are part of the data. Data is equal to US change, summary fit. So this is the summary of results. So that means income is significant, production is not significant, unemployment is not significant, savings are significant, and R square is 0.74 754. So that means 75% variability could be explained by the model. Fitted values. Now fitted values, because our model is fit dot, it is fit dot cons mr. The model object is fit dot cons mr. So this object, this is the fitted object. So what we are going to do is fitted values, auto plot US change consumption. This is the data of consumption. Series is equal to data plus auto layer, because we are putting the layer. So auto plot here, auto layer, fitted, fit dot cons mr, fitted object, series is equal to fitted, x lab is equal to year, y lab, there is nothing label on y lab. Then GG title, percent US change, percent change in the US consumption, guide, color is equal to guide legend, title, there is no need of legend title. So this graph, this pictures, this is the data, ready the data, and this is the fitted values. This plot of actual US consumption expenditure and predicted US consumption expenditure. C bind, now we are combining the data. C bind, data is equal to US change consumption, fitted is equal to, so we are using C bind, column wise binding of data as well as fitted values both, and then we are making sure using pipe as that data frame, that C bind should be converted into a data frame, because for the requirement of ggplot2 is data frame. So we are changing that into a data frame, and then we are further ggplot AES x is equal to data, y is equal to fitted plus GOM point. So we are adding the points, x lab fitted values, y lab data actual values, GG title percent change, GOM ebb line, intercept is equal to 0, slope is equal to 1. Actually, this intercept and slope is equal to 1 shows here, intercept is equal to 0 and slope is equal to 1. If the data both are matching, fitted values and predicted values, they both are matching, then this plot should be, the point should be around this line. So they are in quite agreement, and that's why the fitting is good. Trending and seasonality. See, beer 2, Australian beer, start 1992. We are selecting this data from starting 1992. Autoplot beer, X lab, megaliters. So this is a seasonal plot, and then we are fitting this, and we are having, again we are going with the same way, and we are having data and fitted values, and then we are having C bind data. Again they are matching to the, here these are the quarters, quarter 1 is this, quarter 2 is this, and quarter 4 is this, quarter 2 is this, and quarter 4 is this. So since they are, so that means fitted and actual values, they are matching, and that's why prediction is good. Test for autocorrelations. We test whether the autocorrelation are significantly different from what would be expected from a white noise process. One test is Box-Pierce test based on the following statistic. Here Q is equal to capital T into, this is the length of the series, and here this is the autocorrelation with the lags K square. So, and This is a modification of this by Legend-Box test. Again the large value, yes, here the large is too large. If the autocorrelation did come from white noise series, then both Q and Q star would have a distribution with chi-square degrees of freedom with H minus K, where K is the number of parameters in the model. If they are calculated from raw data rather than from the residuals of the model, they set K is equal to 0. And C, ARIMA models and stationarity. Before we introduce ARIMA models, we must first discuss the concept of stationarity and technique of differencing in time series. A stationary time series is one whose properties do not depend on the time at which the series is observed. Thus, the time series with trends or with seasonality are not stationarity. The trend and seasonality will affect the value of the time series at different times. On the other hand, a white noise series is stationary. It does not matter when you observe it. It should look much the same at the point in time. In general, a stationary time series will have no predictable patterns in the long term. This plot will show the series to be roughly horizontal, although some cyclic behavior is possible with constant variance. Differencing. See, note that the Google stock price was non-stationary. Compute the difference between the consecutive observations. This is known as differencing. Difference can help stabilize the mean of a time series by removing the changes in the level of the time series and therefore eliminating or reducing the trend and seasonality. So, here autoplot GOG 2000 Y lab. So, this is a plot which shows data is not stationary. Now, if we will make first difference using diff, then see what you get. See, here ACF plot is the original data. Here it is not stationary, whereas this one is the stationary. This one after differencing, this becomes stationary. And these things have been tested using box dot test diff. Before we have test only after box after differencing, and here box test diff after differencing. Lag is equal to 10, type is equal to Legend box, and see the p value shows that the series is stationary, because p value here the h naught is that series is stationary, and we are accepting that because of differencing. So, this is all about today's, and this concludes my now random walk and other things are there, but I am not going to discuss these things. These things you can get from the book of fpp3. This is a great book to learn, that is a great book to read. So, this is all. My lecture finishes on time series analytics with R.